Hello everyone and welcome to Course Bridge. Today we are diving into the world of Laplace transform. If you are a student studying mathematics, engineering or physics, you've likely come across this tool before and how powerful it is in solving complex problems. But what exactly is Laplace transform and why is it so important? This video will be an introduction to Laplace transform and how it can be used to solve complex problems. But before we get into the details, let's start with the basics. Laplace transform is a mathematical tool that allows us to take a function that is defined in time domain and then transform it into a function defined in frequency domain. With this, we can analyze the behavior of systems that evolve over time by converting them into simpler expressions in frequency domain, and this also allows us to solve ordinary and partial differential equations easily. But fear not, while Laplace transform may sound complex, we will take it step by step in this video and break it down into easy to understand concepts. So whether you are a student trying to wrap your head around this for the first time, or you are here looking for a refresher, you are just in the right place. So let's get started. Now that we've understood the basics of Laplace transform, mathematically, how does Laplace transform takes a function in time domain and transform it to function in frequency domain? So let's say we have a function defined. We have a function f of t that is defined for all possible defined for all positive values. To transform this function from time domain to frequency domain, what happens is this function is multiplied by e raised to minus st and then integrated from 0 to infinity. This is what we call the Laplace transform of f of t. So please take note of this. The Laplace transform of a function in time domain simply multiplies the function by e raised to power minus st and integrate the new function from 0 to infinity, provided that the integrand exists. So moving on, now that we've seen how Laplace transform works on the time domain function, let's look at some important formula that we'll need moving on when we start solving complex problems on Laplace transform. The first one is 1. So Laplace transform of common So let's start from 1. So if f of t is equal to 1, what is the Laplace transform of f of t? Well, this is simply integral of 0 to infinity e raised to power minus st times 1, which makes no difference. We have this, and now we only have to integrate this and put the boundary value. So we have this going from 0 to infinity. When you integrate e raised to minus st, you get e raised to minus st over minus s. And putting our values here, we have e raised to power minus infinity t over minus s. Then we have minus e raised to power minus 0t over minus s. E raised to power minus infinity gives us, well, it tends to 0, so we can just take this as 0. So we have minus here, this gives us plus, and e raised to power 0 here gives us 1. So we have Laplace transform of f of t when f of t is 1 is equal to 1 over s. Another one, we have f of t equal to e raised to power at. So how do we find the Laplace transform of this? So basically, we have Laplace transform of e raised to power at will be equal to integral of 0 to infinity of e raised to power minus st times e raised to power minus e raised power at rather dt. So how do we integrate this? First of all, this can be simplified to give us e raised power minus st plus at dt. And from here we can factorize our t outside, so we have integral of 0 to infinity e raised power t, we have minus s plus a, and then we have dt. So when we integrate this, we get e raised power minus we still have t, we have minus s plus a all over minus s plus a, and our boundary values here we have 0 to infinity. Now plugging in our boundary values, we have e raised power infinity will give us 0 like it gave us before, so we have negative of e raised power 0 into minus s plus a all over minus s plus a, which is going to give us minus 1 over minus s plus a, which is something as having 1 over s minus a. Alright, another one that we could have is number 3. Let's find the Laplace transform of cos hyperbolic cos. We have cos t. So to do this, we can express cos t in terms of exponential function. And remember that cos t is equal to e raised power t plus e raised power minus t whole over 2. Now let me add a here. So cos at, so we have e raised power at, e raised power minus at all over 2. So now how do we find the Laplace transform of this? Well, the first thing we could do is separate it. So what we have here is something as us having 1 over 2 Laplace transform of e raised power at plus 1 over 2 Laplace transform of e raised power minus at. And from here we get, remember we already found the Laplace transform of e raised power at, and that gave us 1 over s minus a, which means everything here is equal to 1 over 2 s minus a. Then we have plus, well, since we're having positive here and that gave us a negative value here, it means if you have negative now we should have positive, and that means that what we have here is 1 over 2 1 over s plus a. Now what do we do from here? Or we could factorize 1 over 2 outside. We have this, we have 1 over s minus a plus 1 over s plus a. Now taking the LCM, we have 1 over 2, then we have s minus a. Well, s minus a and s plus a, the LCM will give us difference of 2 squares, so we have s squared minus a squared, and above we have s plus a plus s minus a. Well, a cancels the a, so we are left with s plus s giving us 2s, and we have about 2 here giving us s because 2 cancels out. So this gives us s all over s squared minus a squared. So number 4, we have Laplace transform of hyperbolic sine function of at. Now, I'm not gonna prove this because it's very similar to the proof for cos, but I'll give you a clue. Just remember that your sine or your hyperbolic sine function is equal to e raised power t minus e raised power minus t all over 2. So using this and using a similar logic like I used for cos, you should get a over x squared minus a squared. Number 5. Let's find the Laplace transform of cos at. Well, for cos, we also need to express cos in terms of exponential function. Remember that cos at is equal to e raised power AIT plus e raised power minus AIT all over 2. So it means what we have here is Laplace transform, or 1 over 2 Laplace transform of e raised power AIT plus e raised power minus AIT or high AT, whichever way. So from here we can, let me erase this off. So from here we have 1 over 2 the Laplace transform of e raised power AIT plus Laplace transform of e raised power minus AIT. So what does this give us? Means from here we have, remember that for e raised power AT, the Laplace transform is equal to 1 over s minus a. So bringing that here, we have AI now. So we should be having 1 over 2, 1 over s minus, well, let's call that IA, then plus, here we have a negative, so we have positive here, so we have 1 over s plus IA. So how do we simplify this? So we have 1 over 2. Now the LCM of these two will still give us difference of 2 squares. So we have a square, and we have minus IA all square, which in turn will give us plus. But let's continue. From here we'll have s plus IA plus s minus IA. So we have 1 over 2 2s over a square plus a square. Now we're having plus because square of square of I is -1, which cancels out the plus, cancels out the negative we have here to give us plus. So we are left with s over x squared plus a squared. Now similarly, you should have already seen the pattern from hyperbolic sine and hyperbolic cos. We had a here for the sine, and for the cos we had s. So similarly, for sine 80, the Laplace transform is equal to a over a square plus a square. But you could prove it. Just remember that your sine 80 is equal to 1 over 2i times e raised power AIT or high AT minus e raised power AIT. Yeah. So you can use that to prove it. And okay. So do you have any other proof? No. So yeah, let's take questions and apply what we've learned so far on them. So example 1. Let's find the Laplace transform of a function f of t, where f of t is equal to t over k when 0 is less than t, less than k, and we have f of t is equal to 1 when t is greater than k. So this is a piecewise function. So how do we find the Laplace transform of this? Remember, a Laplace transform is simply taking the function and multiplying it by e raised power minus st, and then integrating it from 0 to infinity. But now you see that this is a bit different in the sense that they've given us a boundary here, and they've given us another boundary here. So the Laplace transform of f of t here will be equal to the Laplace transform of t over k, given this boundary 0 to k, plus Laplace transform of 1. Well, we have a boundary here, t more than k in this case. So what does that tell us? It means that if we are doing our Laplace transform here, we would have integral of 0 to k, not infinity, 0 to k, t over k multiplied by e raised power minus st. then plus k to infinity because it's going from k above, and we have 1 times e raised to power minus st. I forgot my dt here, so I have dt here, I have dt here. So what will this give us? Let's integrate. So from here we could do integration by parts, but let me simplify this further. So we'll have 1 over k integral of 0 to k c e raised to power minus st plus integral of k to infinity e raised to power minus st dt. So from here, what do we get? We have 1 over k. So if we are saying t and we are saying e raised to power minus st here, we can apply our integration by parts. And like I explained in the last 2 videos, I think. So integrate by parts, you have integral of u dv equal to uv minus integral of v du. So our u is t and our dv is e raised to power minus st. So we have t. If our dv is e raised to power minus st, what is our, so we have t, and the integral of e raised to minus st will give us e raised to power minus st all over s, no, minus s. Then we have minus integral of e raised to power minus st over minus h, which is our v, and our du is differential of t, which is 1. So we have this here. Then plus integral of this, we have integral of this is straightforward, so we have our boundary here 0 to k. We have e raised to power minus st all over minus s. So let's continue. We have 1 over k. We have t e raised to power minus st over minus s. Then integrating this again, we have minus e raised to power minus st all over x squared, because we're going to have minus s times minus s, so we have x squared. Then our boundary value here is 0 to k, right? And here should be k to infinity, not 0 to k. It's k to infinity. Okay, so k to infinity. So let me just walk around this right here. So if we plug in the boundaries here, what do we get? We have e raised to power minus infinity, which will give us 0 already, over minus s, which is 0. So we're going to have 0 minus e raised to power minus sk over minus s. This should give us plus. So we already have this here. We have e raised to power minus sk over s. So let's work on this here. If you plug in k as t, what do we get? Let's see. We have 1 over k. We have k e raised to power minus sk over minus s, and we have e raised to power minus sk again over x squared. Then when we plug in 0, we have well, the first thing here, everything here will give us 0. When we plug in 0, then we'll have a negative sign here, which would cancel out the plus we meant to have. This is what I'm saying. You have minus this 0 minus e raised to power minus sk over, this is 0 now, so we have 0. Let's just put 1 there. So let me put this as 1. So I have 1. So a few seconds, let me wrap this up. We have e raised to power minus sk over minus s. So let me just put this here, minus, and then we have minus e raised to power minus sk over kx squared. Then we have plus 1 over kx squared. Now remember that we had this before, so we're having this. So we have plus e raised to power minus sk over s. Now these two should cancel out to the same thing. So this gives us 1 over k x squared, that's a mistake, minus a raised power minus sk over k x squared. We can now factorize 1 over k x squared. How do we have 1 over k x squared? Then we have 1 minus a raised power minus k s. Our final answer. So I hope you guys understood that. Let's take one more question. This is a very simple one. So if is equal to 1 plus cos 2t, how do we find the Laplace transform of this? It is very simple. So it's simply equal to the Laplace transform of 1 plus the Laplace transform of cos 2t. So remember from our proofs earlier that Laplace transform of 1 is equal to 1 over s. So we have this here directly. And remember that Laplace transform of cos 80 is equal to s over a squared plus x squared. So we have, and our area is 2. So we have s over 2 squared plus s squared, giving us 1 over s plus s over 4 plus x squared. And then when we take the sum of this, we would have s into s squared plus 4, and so we're going to have 4 plus x squared plus s squared, giving us 4 plus 2x squared over s into s squared plus 4. That's all. So moving on, we're looking at one more theorem for Laplace transform, or basically one more property that we need to know. We still have a lot for now, but for now let's look at one more, and that is called the first shifting theorem. It's called the what? The first shifting theorem. So how does this work? So the theorem, this is it basically. We have, if you have Laplace transform of f of t to give us f of s, which is us in the frequency domain. Now we are saying that if you multiply this by phase shift of e raised power at, we'll be getting f of s minus a. So yeah, let's prove this before we start using it. So let's look at how this can be proved. So we know that Laplace transform of f of t is simply integral of 0 to infinity e raised power minus st times f of t dt. So basically f of t now altogether is e raised power at and f of t. So it means that Laplace transform of this itself is equal to integral of 0 to infinity e raised power at e raised power minus st, then f of t dt. From here, what do we have? We're going to have 0 to infinity. We can apply the law of indices here. We're going to have a t minus st f of t dt, which would give us integral of 0 to infinity of e raised power t e raised power minus t s minus a. If you expand this, you should get this back. So we have f of t dt. So if we assume that let's say r is equal to s minus a, it means that what we have here is simply integral of 0 to infinity of e raised power minus rt f of t dt, which in turn would have been f of r, but then r itself is equal to what? S minus a. So this proves that whenever you multiply your function is already multiplied by a phase shift of e raised power at, where it could be any constant, what you can do simply is to find the Laplace transform of your f of t, and your final answer, replace every occurrence of s there with what? S minus a. Let's take a simple question to illustrate this. So we have f of t equal to a raised power minus t cos squared t. How do we find the Laplace transform of this? So the first thing, like we can see here, we have cos squared t, which is the main function, multiplied by what? A phase shift of e raised power minus t. So let's neglect this for now. The only thing that we need from here is the fact that a is equal to minus 1. So what do? Go ahead and find the what? Laplace transform of cos squared t. So let's find the Laplace transform of cos squared t. To find the Laplace transform of cos squared t, what we can do to make our work easier is to express cos squared t in a simpler trigonometric expression. So we should know that cos squared t is equal to 1 plus cos 2t all over 2, which means from here we are basically finding the Laplace transform of 1 over 2 plus Laplace transform of cos 2t over 2. And that's simply 1 over 2 Laplace transform of 1 plus Laplace transform of cos 2t, which is equal to 1 over 2. Then Laplace transform of 1 by now, we should have known that is what? 1 over s. And for cos 2t, remember it is s over s squared plus a squared. Now we're going to having s over s squared plus 2 squared. So this will give us, we already solved this before, and we got 1 over 2. If you take, let's take the LCM, we're going to have s into s squared plus 4. I'm going to have s squared plus 4 plus s squared. It's giving us 1 over 2 into 2s squared plus 4. And then we have s into s squared plus 4. And we can simply factorize 2 out. So we're going to have x squared plus 2 over s into s squared plus 4. So now that we are done, and the fact that we have realized that our a is minus 1, we simply replace every occurrence of s here with what? S minus 1. But remember that it's usually s minus a. So now we need to be very careful. That's going to be s minus a, which is what? Minus 1. So we are actually replacing s with what? S plus 1. So our final answer, Laplace transform of e raised power minus t cos squared t is equal to s plus 1 all square plus 2 over s plus 1 multiplied by s plus 1 all square plus 4. You can simplify this if you want, but hey, I'm stopping here. So that is, guys, we've looked at an introduction to Laplace transform, some basic Laplace transform that we should get ourselves accustomed to, and basic examples, and also fourth shift theorem and how it can be used in solving problems. So in our next tutorial, we'll continue to look at other theorems like Laplace transform of differential and integration of functions. And yes, we'll look at more theorems in the next tutorial. So please watch out for the next video. If this is your first time on the channel, please like, subscribe, comment, and share to your friends that you think would need a video like this. Also, if you have any difficulty in any subjects, feel free to pick the topic or the course in the comments, and our team members here would go over the course and sort of make a video on them to address the issue you've specified. So that is for today, guys. Catch you guys in the next one. Bye.